Break was good. I was able to catch up on a lot of stuff, sleep, work a little bit, relax a little bit. So it was good. Watch. Are you talking about the Final Four game? Oh no, the Godzilla movie. Oh no, I did not. I think I've seen more memes of that movie than anything. Yeah, the only thing on my mind right now is the Final Four game, man. So I went to college at UCLA, and so I had a vested rooting interest in that game, um, and so I can say I was very sad for for basically all of Saturday night, but man, it was a crazy game. Glad I was able to watch it. Really proud of the basketball team. It's funny because like I tilted on the edge of the planet a little bit. Yeah, I was very sad, that's for sure. But now that pain is done, I feel mostly proud of the team because I started going to UCLA back in 2009. And it really felt like UCLA basketball was just really disappointing, like all through like 2009, like all the way up until now. Like they had a lot of good players, like they had a lot of good NBA players, but like ever since Ben Howland left, it really felt like the program was just really disappointing. And I kind of stopped following it for a few years too. But this year, seeing how far they ran in the tournament and just seeing how they played, really made me a fan again. So I'm really excited for the future. Yes, yeah. So the coach, he's in his second year, I think. I think last year was his first year. I think they had a pretty good season last year too under him, but of course, the tournament got canceled because of COVID. So yeah, they have a he's like a Midwest guy, so he's like from Ohio. So at first, I think a lot of people really criticized the hire because I think the way he coaches like very like rough and tough and brutal kind of basketball, which I guess which is usually not UCLA style. Because the last guy that did that was Ben Howland, and he was basically run out of town because the players didn't really like playing that style. So everyone thought this was going to be Ben Howland part two, but he's been fantastic. Sample project. Oh shoot, yeah. Oh, I forgot to do that. Yeah, let me. Did I give you? I gave you guys samples for 417, I think, right? Um, okay, yeah, I forgot to do it for 410. Yeah, I'll definitely give you guys sample projects. It's definitely something I forgot to do. Yeah. Okay. Yeah. After the lecture today, I'll put up sample projects, so it'll be up by tonight. No, no, I don't bet any money on that. So any rooting that I do is purely just from a fan's point of view. Um, my dad was into gambling for a while, but he's and it's just very light too. But it's mostly just for fun. But yeah, I'm not really into any betting. Nice. Do you have the urge to buy any Microsoft products?
Strong urge to buy all Microsoft products.
Then the
Buy more
microchip is working then. I actually just got my second dose yesterday too, so I'll admit I'm not 100% here because I definitely feel pretty feverish and pretty tired, um, but I at least am cognizant. And
I'll
so
let
We
you get
don't
off
need
to
to
the
have
first
class
dose.
today.
wait, say again.
I said we don't need to have class today. If you don't feel good, it's okay.
No, we need to have class, otherwise we're not going to finish up here. Okay, so it's 5:30, so let's go ahead and get started. All right, so good evening, everyone. How's everyone doing after the break? My iPad just disconnected. Yeah, it's yeah, always breaks always too short, huh? It's never it's never a never long enough to do everything that you want, but yeah, it does feel like that. Like you kind of blink and then it's the break's already over. But we're back, and we have 6 more weeks to go, and so from here, it's time to kind of put our nose down and finish up the semester. All right, so my iPad's freaking out right now, so let me do some announcements. Yeah, 6 more weeks. Yeah, weeks 11 through 16, and then finals week. So technically 7 more weeks, but 6 more weeks of lecture, and then a finals week, and then that's it. Yeah. Okay. So I graded your homework fours over the break, um, and you can see, you should be able to see the scores for those. Um, um, yeah, maybe it's detecting that. Um, And so homework five is posted as well, and so you should be able to see that on Canvas. And so I think homework five is going to be based on diffusion with finite volumes. And so we're not quite done with diffusion with finite volumes yet, and so we should finish that up by Wednesday. And so I made homework five due next Friday. Okay. And so you'll have until then, but I think you should be able to get a good, decent start, especially after the lecture today. After the lecture today, you should be able to get a pretty decent start at the very least through the 1D problem, which I think is kind of the first part of problem two and the first part of problem three. Okay. All right. And so let's see. So any questions that I can answer while I try to scramble and get my iPad back up and running? The project. So the project is going to be due after finals week, and so I think I set the due date to be May 23rd, which I think is going to be the Monday after finals. And so because I know finals week is always really crazy for you guys, and so I want to give you guys a little bit extra time after that, so you can take care of senior design or whatever else you have to take care of during finals week. Then you have that extra weekend to finish up this class as well. And so I give you guys until then. Of course, you're welcome to tune in earlier if you're already done with it. That's fine too. But the 23rd is kind of the latest that I can push back. That still gives me enough time to grade it, because I think grades are typically due kind of a week after finals, and this isn't the only class that this isn't the only class where I have a final project due, and so I need basically I give myself those 3-4 days on that week after finals to finish up the grading. So that Monday is kind of the very last day that I can do it. Have it due, to finish grading everything in time. Okay. So iPad's still freaking out. Maybe my iPad, found out that I got the second dose today, and he wants to take a day off too. It was weird. I was just connected, and then it disconnected me.
Because it knows you're not feeling good, so it wants to give you a break.
How thoughtful.
Right?
All right, let's try this. It feels like it's having trouble connecting to Fullerton. You know, I had the creepiest thing happen. So I was hanging out with some of my friends on Friday, and we were hanging out over Discord. And then we watched this video. I won't say what the video is because it's not the it's not the most appropriate. But you know, we were watching it over another friend's computer that he was streaming. And then I come back the next day and I open up YouTube. And I haven't watched anything that's like even remotely related to that content. And then somehow YouTube suggested a video for me that's exactly what we watched before, which was really creepy. Yeah. Okay. Yeah, it's freaky. Let me try one more time to sign in here, and if not, I'm gonna go ahead and lecture from my laptop because that's at least seems to be working. Make sure I get my password right.
Are we covering lecture notes 9 or 10?
We are on lecture notes 10, so we're about halfway through with it. Sign in. Yeah, that's a good idea. I mean, I've lectured so much on Zoom that, you know, probably whoever is interested knows what I look like and sound like anyway. Okay, that's not working. So I'll try again throughout the lecture, but let me, I know it's not ideal, but I'm gonna go ahead and share my, my laptop screen here and we'll go off this. I have a MATLAB code to show you anyway. So I know this isn't ideal and, you know, I know it's kind of a lot to write down, but I'll go slowly just so that, you know, just so you guys have time to write it down. Okay. Okay. And so this is kind of, you know, I know it's kind of been a while since we, you know, looked at this stuff. And so let's kind of take a few steps back, right? And so where we left off a few weeks ago was we were learning about the finite volume method, right? And so just to kind of refresh your memory, you know, finite volumes is this other computational method that's out there that will basically allow you to run simulations of heat transfer phenomena. So we're in lecture notes 10, but we're on the kind of the beginning of lecture notes 10 here. And so lecture notes 9 was just kind of finite volumes in general, but we want to start with kind of diffusion with finite volumes. Okay. Okay. And so you know, so this is kind of the problem that we're working with here. And so basically we have our differential equation here, and so we have minus k times d dx of d phi dx is equal to q of x, right? Because remember, our diffusion equation here is always governed by our second order derivative, right? And so if you remember kind of from finite differences, the diffusion term was kind of the first one that we did. It was always the second order derivative, okay? And all I did in this case for finite volumes was I kind of split it up where now, you know, I pulled kind of one of the derivatives out from this, and so we have d dx of d phi dx, and so if you combine it together, you get the second order derivative. Okay, and k, of course, here is our diffusion coefficient, and so the higher the k, the more effective our diffusion is going to be. Okay, okay, and so that's the equation that we're working with. And remember, the way that we analyze problems with finite volumes is that we basically take our equation and then we integrate it over a cell, right? And so if you kind of remember the analogy that we went over before the spring break, you know, instead of looking at the grid points in our mesh, what we're looking at instead is kind of the spaces in between the grid points, right? So just like the arrow in the FedEx sign, right? So the arrow is kind of in the empty space in between the D and the E in the FedEx, and so this is kind of the same thing, right? And so for a 1D case, we're basically looking at the space in between two different grid points here, and this kind of defines our cell, right? And so our cell here is defined on the left-hand side by x sub L, and so that's the left side of our cell, and then the right side is x sub R, right? And then in our finite volume method, basically what we're going to be doing is we're going to take our governing equation here and integrating that over the cell, right? And so we're basically taking each term of our equation and integrating from XL to XR, okay? And then from this, we'll be able to evaluate all the terms using our, our integration rules. And then from there, we'll be able to produce an algebraic equation from this, right? And so, because, even though we're using a whole different method here, the goal was still the same. So the goal is to always take, a differential equation like this and turn it into a series or a set of algebraic equations that we can solve. Okay. Let me zoom in a little bit so it's a little bit easier to see. All right. Okay. And so the goal is basically to take these integrals here and apply some tricks if we need to. So remember, with finite volumes, we have these finite volume tricks. Apply them if we need to basically simplify this integral and then to get an algebraic equation. Okay. All right. Any questions on this? Okay. All right. And so let's go and continue on. Okay. All right. And so in this case, we assume, we're going to assume the diffusion constant is constant. And so we're going to pull it out of the integral, right? And so all we're doing is we're integrating this ddx of d phi dx dx, right? And so in the 1D case, this is actually a pretty simple case, because all we're basically doing is integrating this guy. And since we have a dx here, these two guys are going to cancel out, okay? And then we're just going to basically end up with this this guy right here, right? And so we have basically the derivative d phi dx, and we're going to be evaluating that on the right side of our cell, okay? And so that's one term. And then from that, we're going to subtract d phi dx at the left side of the cell, right? And so all we basically did was we just evaluated that that integral, and then we ended up with that, okay? All right, and so that's one side of the equal sign. And then on the other side, we have our source term, right? And so our source term, the way that we perform this integral, because, q of x can be almost anything. And so q of x can really be, any function that you can imagine. And so, usually we don't like to perform integrals. And so, what we did instead was we're going to use our trapezoidal rule, right? And so the way the trapezoidal rule works is that you evaluate your function here, or your integrand. You evaluate it at the midpoint or the centroid of your cell. And so in this case, it's basically the midpoint between XR and XL, right? And then we multiply it by the, either the length or the volume or the area of the cell, okay? And so since we're in a 1D case, we're going to evaluate it at the, or multiply by the length of that cell, okay? And so when we put it all together, we end up with this equation right here. And so we have minus K times, our derivative quantities here. And then on the other side of the equation, we have our source term evaluated at the centroid multiplied by the length of the cell, okay? All right, so any questions on that? I'll just kind of review from before, but I know it's been a while. And so I want to review it while I stall for more time to try my iPad again. Two-factor authentication. Okay, and so that's the that's that thing, right? Okay, and so our next goal is to basically evaluate what's on what's on here, right? And remember that we want to evaluate things in terms of values at the centroid of our cell, right? And so we're thinking of if this is our mesh right here, or this is our grid where we have 6 different cells, we want to solve for things where we solve for the solution values at the centers of these cells, right? And so basically where all these numbers are. Before, what we did was we solved for the solutions at the at the grid points, right? But now instead we're solving them at the cell centers, and so that's one of the big differences that we're going to have here for finite volumes, right? 194 sigma 2 0. Okay. And so since we have 6 different cells here, we will have 6 different equations, right? And so that's basically what we're aiming for, right? And so we're going to look at this, one cell at a time, okay? And then, from that, we'll be able to get all of our equations. All right, my iPad is back, and so let me go ahead and switch to that. That was really weird. Okay, so let me go ahead and draw what we had up there. Okay. Right, and so we had a situation like this where we had cells just like that. So in my vaccinated stupor, I only drew 5 cells, but you can imagine that there's 6, right? Okay, and we're going to evaluate, and we're going to consider these kind of one cell block at a time, right? And so in order to basically solve our system, we need to kind of look at these in terms of our cell in question. Okay, and so let's consider cell number 2 here, right? And then we're also going to need its left and right neighbors. Okay, and so anytime we're doing situations in 1D. At least for now, we're going to consider things in a kind of a 3-cell window here, right? Where we have cell C, where C is kind of the cell of interest, and so that's kind of the center cell. We have uppercase L, which is the left cell, and then we have uppercase R, which is the right cell. Okay. All right, and then what we're going to do here is remember, from our integral equation, we need to evaluate d phi dx at these locations. Right. And so the way we did that is we used a finite difference approximation for these derivatives. Okay. And so basically what we're saying is that on the left side, and so we have d phi dx, and this is evaluated at xl. Okay, we're going to use basically a forward difference scheme for this, right? And so this is going to be phi sub c minus phi sub l all divided by delta x, where delta x is this distance right here, right? We're going to use delta x as basically the same thing, and so it's going to be either the size of the cell or the space between the cell centers. Okay. And then we have d phi dx at x is equal to xr, and that's going to be a forward difference scheme between the right neighboring cell and the center cell. Right? And so this is going to be phi sub r minus phi sub c, okay, divided by delta x. Right? And so at this point, what we can do is we can plug this into our finite volume equation. And then from there, we'll be able to evaluate the left-hand side as an algebraic expression, okay? All right. And so just because, I had to stall so much at the beginning today, so I'm going to go ahead and skip a little bit, okay? And so once we plug that in, and then, we've already kind of evaluated the right-hand side, what we get is the following. And so we have phi sub r minus 2 phi sub c plus phi sub l. All right. This is going to be equal to minus delta x squared divided by k times Q at XC, okay? And this was our finite volume equation for 1D diffusion. Right. And so what we can do is we can take this and apply it to all of our interior cells. Okay. And so that's how we did the interior cells. Okay. And once we do an example later, you'll kind of see this in action. Right? But I think where we specifically left off last time was how to apply the boundary conditions. And so this is kind of where finite volumes really takes a big departure from finite differences, at least in terms of implementation details. And so, underneath everything, it's still the same equation, and so you should still get basically the same answer. But just the way that you apply the boundary conditions for finite volumes is a little bit more involved than what we did for finite differences. Okay? And this is especially going to be true for once we start to get into 2D, which I'm hoping to get to a little bit today. Right? And so first, let's cover how to do, or let's kind of review how we did Dirichlet boundary conditions. Okay. And so Dirichlet boundary conditions, remember, what those were situations where we have the solution value being directly applied. Okay. And so we had a situation that basically looked like this, right? And so, let's say that we have these cells right here. So this is going to be cell 1. This is cell 2, right? And so on the left side of this domain, let's say that we have a prescribed Dirichlet value of phi naught. Okay? All right, and so what this is going to do is it's going to affect how we compute the derivatives at the cell boundaries. In particular, it's going to affect how we compute the derivative on the left cell boundary. Okay. And so it's going to change and so, the big difference, between finite volumes and finite differences is that in finite volumes, when we apply the boundary conditions, what it's going to do is it's going to take this equation that we have up top here, and it's going to modify it, okay? And so if you remember from finite differences, when we applied the boundary conditions themselves became equations, right? And so that's not going to be the case with finite volumes. So in finite volumes, the boundary conditions are only going to modify this set template, okay? And so it's kind of one of those things where it's actually more convenient to do in code than it is by hand. But of course, it's always useful to do things by hand first, just to kind of get the idea. Okay. All right. So any questions on this? Okay. All right, so let's go ahead and see how that affects things, right? Because normally we have this on the left-hand side, right? So we have minus k times d phi dx at xr minus d phi dx at xl. Okay, and the right-hand side, is going to be the same. I'm not going to touch that side. Okay. All right, and so if we have a cell that's on the boundary like this, where the Dirichlet is on the left side, okay, what that's going to do it's going to modify how we evaluate this integral here, or this derivative here. Okay. And so for the right side, you know, we're just going to use the same thing because we have a right neighbor, right? And so our right neighbor is going to be fine. And so we're going to have minus k times phi r minus phi c divided by delta x. Okay. And then on the left boundary, you know, we're gonna do a finite difference approximation here, but instead, you know, we're going to use our prescribed value. Okay. And so we're going to have phi sub c minus phi sub o. Remember, phi sub o here is that's our prescribed value, okay? And then we need to divide by the physical distance in between the self-center and the Dirichlet boundary, right? So let me kind of draw it here just to kind of show you, right? Okay. And so normally, you know, we're going self-center to self-center, right? And so this distance here between phi c and phi r, this is delta x, right? Because that's kind of our grid spacing. But when we go between phi sub c and phi naught, this distance here is only half that because we're only traveling half a distance from the middle of the cell to the boundary, right? And so this distance right here is delta x divided by 2, right? And so when you go and apply your finite difference, you know, we need to divide by delta x divided by 2. Okay? And of course, this is equal to the right-hand side, which we don't care about at this point. Okay. And so if we evaluate this, you know, these terms here, what we get is phi r minus 3 phi c, right? Because now we have 3 because we have this 2 right here. Okay. Plus 2 phi naught is equal to whatever's on the right-hand side, which is our source term. Okay. And then at this point, since this phi naught here is a known quantity, basically we know its value already. Okay. What we can do is we can move that to the right-hand side. Okay. And then once we do that, this will give us our equation for the Dirichlet boundary, which is on the left-hand side. All right. So any questions on this? Okay. All right, so that's how you do Dirichlet boundary conditions. And now let's do Neumann boundary conditions. And so for Neumann boundary conditions, it's going to be, you know, roughly the same idea here, except it's going to be a little bit easier. Okay. All right. And so for Neumann boundary conditions, remember the way that we described them before was that this was kind of the derivative of our solution at the boundary, right? Or so that's what we're specifying. But for finite volumes, the Neumann boundary condition takes a slightly different meaning, mostly just for kind of convenience, especially once we start adding convection into the mix. And so our Neumann boundary condition kind of takes this slightly different meaning where instead of specifying the solution at the boundary, what we're doing instead was we're going to be specifying the flux of the solution at the boundary. Okay. And so in this case, you know, when it's just diffusion, it's just going to end up being just the derivative. But once we start adding convection into the mix, you'll see that, you know, we're going to basically lump together the convection and diffusion terms, and that's going to be our Neumann BC. Okay. But for just diffusion, you know, this is basically what we're going to have. Right. And so for a pure kind of diffusion case, either for 1D or 2D, what we're basically going to say is that d phi dx at xb, where b is going to be the boundary, is going to be gamma, which is our condition. Right? And so let's say, for example, let's say that we have a Neumann boundary condition on the very right side of the domain. Okay, and so we have a situation that maybe looks like this, right? Okay, and so this is going to be cell C, and so that's going to be our cell in question, and we're also going to have our left neighbor. Okay, and on the right hand side of the cell, we're going to say that this is going to be gamma. Okay, where gamma is of course known because it's a boundary condition. All right, and so let's go back to our finite volume expression, and let's see how this modifies things. Okay, all right, and so kind of before we plug in our finite difference approximation, our finite volume equation looks like the following. And so we have minus k times d phi dx at x is equal to xr minus d phi dx at x is equal to xl. Okay. And this is equal to the right-hand side, okay? Which again, you know, is important, but for now it's not important. So I'm just going to leave this dot, 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 okay? All right. And so since this Neumann condition is on the right side of our cell here, what we're going to do is we're going to replace this derivative here with the Neumann condition. And then the other derivative is fine because we have our left neighbor there, and so that's still good. Right? And so we have minus k times. We're going to replace this entire derivative here with gamma, which is our Neumann value. Okay. Okay. And so then we have that, where on the left-hand side we still, or for the left of the cell, we still have our finite difference here. But now we just replace that right derivative with gamma, okay? And just like we saw with the Dirichlet boundary condition, since this gamma here is a known quantity, we can go ahead and move that to the right-hand side. Okay. And that's going to give us our finite volume equation for that cell on the very right, for that case. All right, so any questions before we do kind of a full example, both with hand calculations and with code? Okay, all right, so let's go ahead and do a bigger example, okay? So I believe this is the same example that we did with finite differences kind of way back when, but now we're doing with finite volumes, okay? And so the equation is the following. And so we have 3 times d squared phi dx squared is equal to 2x squared, right? And then we have the following boundary conditions, right? And so we have 1, which is d phi dx at x is equal to 0 is equal to 0. Okay. And on the right-hand side, we have a phi of 1 is equal to 10. And so for this problem, I want, let's solve for a finite volume solution for 4 cells. Okay. And the domain is given by the following, which is kind of implied by the boundary condition. Okay, so our domain is going to be 0, which is less than or equal to x, which is less than or equal to 1. Okay. All right. And so since we have 4 cells, in the end, we're going to get 4 algebraic equations. Okay. And so our cells kind of look like, basically look like the following. Okay. This is going to be cell 1, this is cell 2, cell 3, cell 4. Okay. All right. And so what we want to do is we want to find the finite volume equations for this, right? All right, and so the first thing that we're going to do is we're going to work on the interior cells because those both have left and right neighbors. Right, and so in this case, we only have 2 interior cells, cell 2 and cell 3, okay? But we can basically just use our finite volume equation just straight up for this, right? And so for those equations, we have phi sub r minus 2 phi sub c plus phi sub l, right, is equal to minus delta x squared divided by 2, or divided by k, sorry, times q at xc, okay? Where q in this case is 2x squared, right? All right. And so if we label this x coordinates of each of the cell centers, x1, x2, x3, x4, I think this should be 0.125. This should be 0.375. This should be 0.625. And this should be 0.875. Okay. Because remember, these are the coordinates of the cell centers, not the grid points. Okay. Clean this up a little bit. 625. Okay, and so if we write this out for cells 2 and 3, what we get are the following equations. So let's start with cell 2. And so cell 2, we're going to start with the right neighbor for cell 2. And so the right neighbor for cell 2 is going to be cell 3, right? So we have phi 3 minus 2 phi 2 plus the left neighbor for cell 2, which is cell 1, okay, is equal to minus x squared, or delta x squared, where delta x here is 0.25. Okay. Right, and then we're going to divide by 3, which is k. Okay. And then we're going to have 2 times x2 squared. Okay. Right, and then we're going to do the same thing for cell 3. So for cell 3, we have phi 4 minus 2 phi 3 plus phi 2 is equal to minus 0.25 squared divided by 3 times 2 x3 squared. Right, and those are our first two equations. All right, any questions on this so far? Okay. All right, and so those are the interior cells, and so now let's do the cells on the boundaries. Okay, so let's that's going to be cell 1 and cell 4. Right. So let's start with cell 1, and we know from the problem statement here, cell 1 has a Neumann boundary condition on its left side. Okay. And so let's do kind of the same procedure as we did before, but now let's put the Neumann boundary condition on replacing the left derivative, okay? All right. And so if you remember from 15 minutes ago, what we did for these cases was we went off this form where we have minus k times d phi dx at the right side minus d phi dx on the left side. Okay. And this is equal to Q at XC times delta X. Right. All right. And so remember, for the Neumann boundary condition, what we're going to do is we're going to replace this entire derivative, right? And in this case, because the Neumann boundary condition is on the left side of cell 1, what we're going to do is we're going to replace, this d phi dx on the left side. Okay. Right. And so we go ahead and plug that in using our usual finite difference for XR. So we have minus K times V2 minus V1 divided by delta X. Okay. And so that stays the same for cell 1 because we have a right neighbor for cell 1, and so that's fine. Okay. But on the left-hand side, what we're going to do is we're going to replace this with gamma, which is our Neumann condition. Right. And for this particular problem, the gamma is actually 0, right? Because that was our Neumann boundary condition. Right, and so we go ahead and fill everything in, and we can get our equation for cell 1. And so our equation for cell 1 is going to be phi2 minus phi1 is equal to minus 0.25 squared divided by 3 times 2 times x1 squared. Okay. Right, and so notice, this didn't become its own equation, and so we basically took our usual kind of finite volume equation, and we just modified it according to the boundary condition. All right, and so next we're going to do our the Dirichlet boundary condition on the right side of cell 4. Before I do that, are there any questions on how we applied this this boundary condition here? Okay. All right. So let's go ahead and try cell 4. Okay. And so cell 4 is on the very right side of the domain, and it has its Dirichlet boundary condition. Okay. All right. And so let's go ahead and do the same thing. As we have minus k times d phi dx at xr minus d phi dx at xl. Okay. And this is equal to qc q at xc times delta x. Okay. All right. But since we're on the right-hand side, we're going to replace this derivative now with the Dirichlet boundary condition. Okay. And so we're going to do the same thing as before, except now we're replacing the right-hand side derivative. Okay. Okay. And so since we're replacing this derivative, we're going to plug in our specified value in for phi naught. Okay. And our phi sub c in this case is going to be phi 4. Right? Okay. The left-hand side derivative stays the same, and so that's that's fine. And let me go ahead and plug in for this guy here. Right. And so we have 2 delta x, 2x4 squared times delta x, which is 0.25. Okay. And of course, k is 3. And phi naught here for this problem is 10. Okay. All right. And so if we go ahead and kind of arrange the math, what we get is 20 minus 3 phi 4 plus phi 3 is equal to minus delta x squared, or minus 0.25 squared, I should say, divided by 3 times 2x4 squared, okay? Man, my iPad's being really weird today. Okay, and so we can go ahead and move that 20 to the left-hand side, and then what we get is phi 3 minus 3 phi 4 is equal to minus 0.25 squared divided by 3 times 2x4 squared minus 20. Okay, and this is our last equation here for cell 4. Okay. All right. Any questions on this? Okay, and so now we have 4 equations for each of the 4 different cells. And so at this point, we could go ahead and put it all together into a single matrix. All right, and so let's look at the matrix form for this. And then after this, I'll show you how it's implemented in code. All right, and so first we're going to write out the equation for cell 1, then the equation for cell 2, then the equation for cell 3, and for cell 4, right? And so for cell 1, remember we had a minus phi 1 plus phi 2. Those are our coefficients on the left. Okay, and then the rest of the equation, or rest of the matrix, looks like the following. Ooh. I'm heating up so much that my hands are sweating and causing problems for my iPad. All right, and so those are the left. That's the left-hand side matrix, and the right-hand side, and the solution vector. And over here, we have everything that's on the right-hand side. Okay, so I'm not going to fill those in. Okay. All right, so that's basically the problem, right? And so now I'm going to go over the MATLAB implementation that I posted on Canvas as well. But and so remember, keep this kind of matrix in mind here, and most of all, kind of remember how we kind of came about this. And so the way that we kind of build these equations is we kind of go cell by cell, right? And so what you'll see from the code is that we'll have a for loop that loops over all the cells. We'll visit every single one. And then depending on if that cell is on the boundary, then we'll do something different for that. Okay. All right. Any final questions before we jump into the code? that is a very small -2. That is correct. Okay, so let's go ahead and switch to the laptop, and let's hope that the iPad doesn't break again. Okay, and so here we are. So here's kind of the written version of the code, and here's the actual version. Okay. Oh, let me increase the fonts because it's a little bit small. I was working on something else today. Where's preferences? Preferences, fonts. Let's do 14. Okay. Move you back up here. Okay, and so here is the code. So it's a short code, because it's just a 1D problem. But let's see how we go about doing this, right? And so if we let's start with kind of the first section here. And so the first section, we are going to set our simulation parameters, okay? And so first of all, you can see that we have this this number n, right? And so before we use this variable n here to denote the number of grid points in our mesh. But now what we're going to use it for is we're going to use it to define the number of cells in our finite volume mesh, okay? Okay, and so that's n. And so I'm showing you an example with 40 cells, but you can go ahead and modify this as much as you want, okay? Right, and so let's do the case with 4 cells just so it matches up with the with what we did on paper, right? Next, we're going to need the locations of all the endpoints, okay? And so you can see I'm using the linspace function here. But as for the number of points that we want n plus 1, right? Because we always have kind of more grid points than we do cells. And so that's why we do kind of n plus 1 there, okay? And then dx here is just going to be, the grid spacing. And so another way that you can do dx is you can just do L, where L here is just 1, and we divide by n. Okay. All right, and so here's another new thing that we see for finite volume problems, is that we need to know the locations of the cell centers, right? And so this function right here will basically return to us the locations of all of those cell centers. And so instead of starting at 0, what we're going to do is we're going to start at 0.5 times dx, right? And so if you kind of remember from the example we just did, our dx was 0.25, and so our starting cell center value is going to be 0.125, which is half of dx, right? And then we're going to go all the way up until 1 minus that same thing, right? So we have L, which is 1 here, minus half of the grid spacing. And so that's how we get kind of the endpoint, and we want n of these points. And of course, we have to define our left-hand side matrix and our right-hand side vector. And so those are right that. And then we have our diffusion coefficient, which is 3 right here. Okay. Okay. And so now we enter the for loop. And so this is kind of where most of the code is going to be. And then from this, you can see that we're going to use the for loop to visit every single cell in our grid. Okay. And that's why we loop from 1 to n, right? And so you can see here we have an if statement that defines different things according to where we are in the grid, right? And so first, let's look at this condition here. So if I is equal to 1, right? And so if I is equal to 1, this tells us we're on the cell that borders the left side, which we apply the Neumann boundary, right? And so in this case, we're going to apply the code that looks like this, where we set the values in the matrix like so, and then we make the right-hand side vector like this, okay? And so you can see this is this formula right here. It looks a little bit complex, but it's basically the same as our dx squared divided by k times 2 times xc squared. Okay. All right. And so this next if statement here is going to check if we're on the right side of the domain, and so that's going to happen when I cell is equal to n, right? And at this location, we're going to apply our Dirichlet boundary condition, right? And so remember, for the Dirichlet boundary condition, we're going to make the diagonal term -3 instead of -2, right? And so we subtract 1 from that due to the fact that we're doing that half cell distance, and then the off diagonal term here is 1, and then we can see here on the right hand side, we have our usual source term here, but we also subtract the 20, which came from the Dirichlet boundary condition. Okay. And then finally, we have our else statement, and so this is for all the interior cells. And so for all the interior cells, we have 3 entries in the in the left-hand side matrix. We have the diagonal entry and both the off-diagonal entries, and of course we have our source term. Okay. And once we reach this point in the code, then the left-hand side matrix and the right-hand side vector are complete, and we can go ahead and solve. And so let me go ahead and run this code. And you can see here, here is our solution, right? And so in blue here, we have the finite volume solution. And I've also plotted for you the exact solution as well, okay? And so let's see how the performance of this code changes depending on the grid spacing, right? And so right now we only have 4 cells. And so, it's a little bit hard to see, but we have 1, 2, 3, 4. And so, there's not much difference here. So those 2 cells are merged into 1. And so let's go ahead and change this to 40. and let's see how that changes things. Okay, and so you can see with 40 cells, we're pretty much right on top of each other, right? And so this looks really good. Okay, and so that's kind of a basic implementation for how you do a 1D finite volume diffusion code. Right? And so any questions on this example before we start working on 2D problems? Okay, right. So this example code is available for you on Canvas, and so it's fully complete, and so you don't have to change anything to it. But you're also, of course, free to change the the number of cells, and so you can play with that to your heart's content. Okay, and this, again, like I've said before, this serves as kind of a good reference and a good example for you once you start working on the homeworks. Okay, all right. So let's go ahead and come back to the iPad. All right, and so now let's start talking about 2D diffusion with finite volumes. Okay. Okay. And so just like we saw with finite differences, the jump from 1D to 2D is a little bit involved. And so we're gonna have to dig deep into our bag of integral tricks here in order to evaluate this guy. But we're gonna walk it through step by step, and you'll hopefully you'll see that it's at least intuitive. Okay. All right, and so let's go ahead and start with our 2D diffusion equation. And I'm going to write this in vector form just so we can easily apply our rules, right? And so our 2D diffusion equation is minus k times the divergence of the gradient of phi, okay? And this is equal to q of x, y, okay? All right, and so just like we always do with finite volumes, what we're going to do is we're going to integrate this guy over a cell. Okay. And in this case, remember we're applying a double integral because we're in 2D space now, right? And so that's why we need the double integral, okay? Right, and so now, we're in a little bit of a different space. And so if you remember in the 1D case, what we could do is we could kind of evaluate this integral kind of just straight away. But since we're in 2D, we're not able to do that. And so what we need to do is we need to take this integral here that I've kind of boxed, and we need to compute and we need to convert this into a line integral using the divergence theorem. Okay. Or I should say boundary integral. Or an integral around the boundary of the cell, which in this case is going to be a line integral because we're in 2D, but I do want to be kind of general here. All right, and so I'm going to go ahead and do that on the next page, and what you'll see is that this kind of transforms into a line integral around the boundary. Okay. All right. Any questions on this? Okay. And so if we apply our divergence theorem, we end up with the following. Okay. So we have minus k. Now we have this line integral here, which remember it looks like a little music note. Okay. And this is now around the boundary of A. Right. And so we have the gradient of phi dot n hat ds. Okay. And this is still equal to double integral of q of xy dA. All right. And so we're going to spend most of our time working on the integral on the left, because that's kind of the one that's more interesting to work with. But let me just show you just really quick how we apply trapezoidal rule to evaluate this integral on the right. Okay. And so remember, we're not actually going to be performing any integration, which is weird to say because we're doing all these integrals here, but we're actually not going to evaluate them. Okay. And so the way that we we solve this is we evaluate the integrand at the centroid of the cell. Okay. And so now we're in 2D, and so this is going to be both the x and y coordinates have to be at the centroid of the cell. Okay. Right. And then we're going to multiply this by delta x times delta y, where this quantity right here, this is the area of the cell. Okay. And so I just wanted to get that one out of the way first because, we're going to kind of forget about it for a while. But, I just wanted to show you how you do trapezoidal rule in 2D. Okay. But from here on out, let's go ahead and start focusing on this integral right here, because this is kind of the one that's kind of most interesting. And so let me go ahead and draw our square here, because that's what our finite volumes look like in 2D. Okay. Right. And so our square looks like the following. Right. And when we're evaluating this line integral around the surface, what we're basically doing is we're taking a path around the edges of the cell. And we're evaluating over all of those edges. Okay. And in particular, for a square like this, we have 4 sides to the square, right? And so we're basically going to be evaluating each side of the cell separately. Okay. All right. And so let me go ahead and start labeling these sides, right? And so the top side of the square, I'm going to call N for north. Okay. And we're going to draw our outward unit normal. And I'll show you what we're going to do with that in a second. Okay. The right side of the cell, I'm going to call east, little e for east. Okay. Okay. And on the bottom, that's going to be our south side of the cell. Okay. And on the left side, we're going to have W for west or west. Right. And our normal vector is going to be like that as well. Okay. And so what we're going to do here is we're going to split this line integral here into 4 separate, 4 separate mini integrals. Okay. All right. And so let's go ahead and do that. All right. And so instead of doing this, let's see, minus k times gradient of phi dot n ds. Okay. What we're going to do is we're going to split this into a north integral, an east integral, a south integral, and a west integral. Okay. All right. So it's going to look like this. Since we have integral on the north of gradient of phi dot n hat ds plus integral on the east gradient of phi dot n hat ds plus integral over the south gradient of phi dot n hat ds plus integral on the west side gradient of phi dot n ds. Okay. And so we have 4 integrals that we need to compute here. Oh, I forgot minus k. And so there's minus k multiplied by all this stuff. Okay. Right. And so we have four integrals here, which makes it seem like we're making the whole thing worse. But you can see that. But you'll see that each of these integrals themselves are fairly easy to evaluate comparatively. Weeb side. That's my side too. All right. So any questions on this so far? Right. And so on the next page, what I'll show you is how to actually evaluate these integrals. So I know it kind of seems a little bit unruly right now, but you'll see that evaluating these is relatively not that bad. Okay? And what's really going to come into play are all of these n hats right here, right? And so there's a reason I drew them into the image here, and there's a reason I have them pointing in the directions that I do, because they're going to play a pivotal role. Okay. And also, before we move on, I know you guys know this, but just for the sake of completion, the height of the cell, we'll call it delta y, and the width of the cell, we'll call it delta x, right? And so a lot of times we assume them to be the same, but for the sake of this kind of derivation, I'm going to have them be separate. Okay. And so we have delta x horizontally, delta y vertically. Okay. All right. And so let me just go ahead and write out one of the integrals that I had before. And so let me just do the north side one just as an example. Okay. And what we want to do is we want to find expressions for all these different integrals in kind of easier terms. Okay. And so let's go ahead and remind ourselves what each of these parts are, right? And by parts, what I mean is the gradient of phi and the outward normal vector. Okay? So let's start with the gradient of phi. Right? Remember, the gradient of phi here is actually a vector, right? And so it's a vector that contains the partial derivatives of phi in each of the directions, right? And so this can be partial phi, partial x, and partial phi, partial y. Okay? And so it's a vector that looks like that. And so that's going to be the same no matter what face that we're on. And so this gradient is always going to take this form. Okay. But what's going to change on each of the different faces is how the unit vector is evaluated. Okay. All right, so let's go ahead and see, how these are evaluated on each face. Okay. All right, and so let's start with the north face, right? And so for the north face, our outward unit vector points upwards like this, right? And so if we put this in vector form, what this looks like is a vector that's 0, 1, right? And consequently, on the south face, the outward normal vector is pointing down. And so one way that we can express the outward unit normal is 0, -1. Okay. Right? And we can do the same for the east and the west sides too. Okay? And so on the east side, our outward unit vector is pointing to the right. And so putting that in vector form, that's going to be 1, 0. And on the west side, our outward unit normal is pointing to the left. And so this gives us an outward unit normal of -1, 0. Okay. All right. And so now that we have the vector component representations of the gradient of phi and each of the outward unit normals, all we have to do is take the dot product at each of the different faces. Okay. And I'll show you just kind of an example of how we can do this on the north face, right? All right, so on the north face, we have gradient of phi. And so gradient of phi is going to be d phi dx, comma, d phi dy. Okay. And so remember that gradient is going to be the same no matter what. And then we're going to take a dot product between this and our outward unit normal. And we know that for the north face, our outward unit normal is 0, 1. Okay. So we're going to dot product with 0, 1. Okay. And then if we evaluate this this dot product here, remember we're going to take each of the components and multiply it by its corresponding one, and then add them all together. Right? And so the dot product is going to be d phi dx times 0 plus d phi dy times 1. Okay. And so for the north face, what we're integrating basically is just going to be d phi dy. Okay. And so this simplifies things pretty greatly for us, because now, each of the different face integrals is just going to have one partial derivative of phi. Okay. Okay. So any questions on this so far? Okay. All right, and so let's perform those dot products with the outward unit normals for each of the different faces of our square. Okay. Right. What we get is the following. Okay. And so this is where we started. And so where we started was we had a line integral around the entire surface, okay, of gradient of phi dot n ds. Okay. And so after breaking this up into the 4 different sides, and performing the dot product as we saw, what we get is the following. Okay. And so we have minus k, and so let's not forget that. Okay. Then we have the integral on the north side of positive d phi dy. Okay. And this is going to be ds plus integral on the east side of d phi dx ds plus integral on the south side. Sorry, this should be a minus. Okay, because remember the dot product for the south side is a -1. Okay, minus d phi dy ds, okay, minus integral on the west side of d phi dx ds. Okay. Right. Right. And so that simplifies our life pretty considerably here. Because instead of evaluating kind of a weird nebulous gradient of phi dot n, now we're just evaluating these integrals, which we can do. And the way we're going to do this is we're going to use trapezoidal rule, a 1D trapezoidal rule. Okay. And so if we do that, we're just going to take the integrand here, evaluate it at the face, at the centroid of the face, and then multiply by the length of that side. Okay. And so if we do that, we end up with minus k times d phi dy on the north face multiplied by delta x. Okay. It's delta x here because remember the north face runs from left to right, and so that's why we're using delta x there. Okay. Plus d phi dx on the east face times delta y. And remember, for the east face, we're integrating from down to up, and so that's why the length of that side is delta y. minus d phi dy on the south side, delta x minus d phi dx on the west side, delta y. Okay. And go ahead and lock this guy. Okay, and right here, unfortunately, we're about 5 minutes out from kind of the punchline here. So I'm gonna have to leave you guys on a little bit of a cliffhanger. We'll go ahead and blame it on the technical difficulties at the beginning, but I can at least give you a hint about where we're going. Is that now that we have these terms here, we're evaluating these partial derivatives on the faces. What we can do is we can kind of do the same thing that we did in 1D and use finite differences to approximate each of these derivatives. We want to approximate these derivatives in terms of the self-centered values. Okay, but that's going to have to wait till next time because we're out of time today. Right? All right, so thank you guys for tuning in today. I apologize for the technical difficulties at the beginning, and so you should be able to get started on homework 5. So definitely start looking at that. And then on Wednesday we'll finish this up. I'll show you how to implement a finite volume code in 2D. Right? So thank you guys for tuning in today. I hope you guys enjoy the rest of your evening, and I'll see you guys on Wednesday. Thanks, guys.
Thanks, Professor.
Thanks, guys. Thanks, Marcos.